Okay, this is video lecture 28.2, part 2, and we're going to focus on section 4 of chapter 28, which is about circulating charged particles. Obviously, we're talking about a charged particle in a magnetic field. That's the topic of this chapter. And circulation is a key word now, right? Circular motion. We're going to get that, as we're going to see. Let's start with the following situation. We've got a charged particle, and it's moving in the plane of the screen here. You can see it there. It's the blue dot. It's got a certain velocity. See the vector there happens to be pointing to the right in the plane of the screen. And that particle has positive charge, Q. Okay? So we've got a positively charged particle. It's got a velocity v, at least at this instant in time. And it's immersed in a region, it's the green shaded region, where there's a uniform magnetic field, B arrow, that is directed out of the screen. And there's all that information there showing you that. That magnetic field region is that green shaded region. And everywhere in that region, the magnetic field is coming out of the screen towards us and has the same value. At this moment in time, for that particle with that charge, with that velocity, in that magnetic field, here's the first question. What is the direction of the magnetic force, F sub B, on the particle at this instant? I'd like you to get an answer for that on your own. Feel free to pause the video, get an answer for the direction of FB, and then come back. Okay, so did you think about that? Did you employ in your thinking this expression that the magnetic force equals the charge Q times V cross B? And all I'm asking for right now is the direction of that force. So we know we've got a vector product, R cross B, so we use the right-hand rule for that. So we have to be able to apply the right-hand rule. Again, I like the two-pen approach. I'll use the red pen for the V and the green pen for the B. And as I'm standing here looking at this, I would hold the V pen horizontally to my right and the B pen straight up towards me. And then I would do the right-hand rule and see which way my thumb points, and that'd be the direction of V cross B. And the direction I get is that direction. Exactly perpendicular to the V and to the B. Okay? Now that's V cross B. We need to label it that way. That's the direction of that vector. And then we have to account for the effect of the charge that's multiplying that. And mainly, is the charge positive or negative? That's the key thing. Well, if this charge is positive, that means the direction of the force, FB, is the same as the direction of V cross B. So the actual force, F magnetic, is that way. Okay, there we go. F magnetic, given by Q times V cross B, is perpendicular to V and perpendicular to B, and given by the right-hand rule. So what's going to happen next in the next moment? Right? That's what's happening right now. What's going to happen? Well, we're going to take that F magnetic to be the net force, right? Means that's the direction, therefore, according to Newton, that's the direction of the net force, that's the direction of the acceleration. Okay, so the acceleration is in the same direction as the force. So the acceleration is, if you like, downward as we look at this screen. That's the direction in which the velocity is going to change. Now the velocity right now is to the right, but the change in the velocity is going to be downward. So what's that particle about to do? Well, it's about to move forward and downward, kind of like that. You see where this is headed? And as it does, its velocity direction is going to change, and therefore the F magnetic is going to change too. Right? Let's look a little bit later, like when the particle is right there. Now the velocity vector is something roughly like that. Now do the right-hand rule for V cross B. The resultant has to be perpendicular to V and to B. And you'll get the magnetic force is that way, which will mean the velocity will arc around that way some more. And there it is a little bit later. And now the velocity vector is that way. And the right-hand rule will give you the direction for the force that way. And so it will arc around. And so guess what you get? You get a circle. And the force is always towards the center, and the velocity is always tangent to the circle. And that's exactly what gives you uniform circular motion. Remember last semester? All right, so the magnetic force Fb is perpendicular to the particle's velocity. So the force can only change the direction, not the magnitude of the velocity. When the force is perpendicular to the velocity, therefore the acceleration is perpendicular to the velocity, you're changing the direction of the velocity, not the magnitude. The result, uniform circular motion. So I've sketched that circular trajectory there, okay? In the region where the field is. And of course, there'll be some center of the circle relative to where it started, and the circle will have some radius, and I'm using the symbol big R for that. And now, let's study that circular motion a little bit more, because we know enough physics to do it. We just needed this magnetic force rule and the second law of motion. So, first, let's use the magnetic force rule to get the magnitude of the magnetic force, Fb magnitude. Well, just go to Q times V cross B and get the magnitude. So Q itself, which is positive, magnitude of velocity, magnitude of magnetic field, sine of angle between velocity and magnetic field. They're like this. The velocity is in the plane of the screen and the magnetic field is perpendicular to the screen. So that's a 90-degree angle. The sine of 90 is 1. Writing everything as a magnitude, it's just QVB. And then put that into Newton's second law for circular motion for the radial direction. Remember this fun formula? A radial equals F net radial over m. Newton's second law when applied to circular motion. And for A radial, we had this wonderful formula we used all the time last semester when we had circular motion. A radial is the speed squared over the radius. Remember V squared over R? And for F net radial, put in QVB, the magnetic force, over m. Then you can cancel one factor of V on both sides, and you can solve for R. And you can get a nice little formula for that radius of the circular trajectory. Quite a few things determine that radius, according to this formula. The mass of the particle, the speed of the particle, the charge of the particle, and the strength of the magnetic field. All right? This is a very handy little result. Okay? Because we're going to have charged particles moving in circles. That occurs naturally, believe it or not, in nature. And it occurs a lot in physics laboratories of one kind or another. So that's a handy formula because that's going to determine the radius of our particle's circular trajectory. The other thing we often like to know is, what's the period, capital T, of the particle's circular motion? Remember, the period is the time to go around exactly once, capital T. And when you go around in a circle at constant speed, the time to go around once, the period, is the distance you go around once, the circumference of the circle, 2 pi r, over the speed. Plug in the result for the r now that we just learned. And your formula for the period is 2 pi over v, mv over qb. And you see there's a v upstairs and downstairs. An interesting thing that happens in this formula for the period of the circular motion is that the factors of v cancel, and the period, the time for the particle to go around once, doesn't depend on its speed, how fast it's going. It depends only on the mass of the particle, the charge of the particle, and the strength of the magnetic field. So this is also a very useful formula. And I want to do a mini example where we apply that thinking, okay, to a laboratory-like situation. Mini example, circulating particle in a magnetic field. Okay, what's happening in this figure? We have a charged particle. Well, it happens to be an electron. It's going to be accelerated from rest through an electric potential change of V equals 200 volts. I'd be more inclined to call it delta V, but this picture calls it V. Okay, so an electron is accelerated from rest by an electric field, and therefore an electric potential difference, and the direction of that acceleration in this particular diagram is that way. It must mean, by the way, that the electric field in here is opposite, right? Because it's an electron with negative charge. But the point is, you can still use an electric field, and therefore a potential difference, to accelerate a charged particle. And the electron will leave there. You have to imagine there's a little hole carved right there in that plate. And the electron can then exit and then travel through this region with a velocity v in a straight line, okay, until it enters this rectangular region over here inside this red dashed box. And inside that region, we have a uniform magnetic field of magnitude B1. And it's either directed exactly out of the screen towards us or into the screen away from us. We don't know which. And then as the charged particle, the electron, enters that magnetic field region, notice it immediately starts to circulate, move in a circle, until it comes around to this bottom point right here at the end of the field region B1, in which point it leaves the field region. And then it moves in a straight line again, going that way, until it enters another region over here, rectangular in shape, in which there's a different uniform magnetic field, B2, either into the screen or out of the screen, we don't know which. And the particle then circulates around that way in a half circle until it exits the whole field region again, going this way. And that's the path it goes. And here's what we know about that. Both those fields, B1 and B2, are uniform. Okay? The fields are perpendicular to the plane of the figure, and they have magnitudes of B1 magnitude is 3 millitesla, B2 magnitude is 6 millitesla. And we want to know several things. The direction of those fields, B1 and B2, into the screen or out of the screen, the radii of those half circles, and the time spent in the second magnetic field, and the electron's speed upon leaving the last field. So they want us to tell them a lot. First, I'm going to find out how fast the electron is moving when it leaves this electric field region that accelerates it. Okay? What is the V after accelerating from rest through that potential difference? And for that, we will just use conservation of mechanical energy. We'll see that the electric force on the electron, I'm talking about when it's in this region here, between these plates, that's really just a parallel plate capacitor. The only force doing any work is the electric force, which is conservative. So K1 plus U electric 1 must equal K2 plus U electric 2, where there's 0.1 and there's 0.2. It starts from rest, so the initial kinetic energy is 0. And I want the kinetic energy at the end, so I want K2. So K2 is, look, I'm just rearranging the formula, U1 minus U2. That's negative delta U, negative change in the potential energy. And the particle's charge is negative little e, so that's, and so this is negative, I'll write it like this, Q delta V, but the Q for an electron is negative little e, so I just get that little formula. K2 is little e times delta V, or just V. Then of course K is 1/2 m little v squared, so we have that. So I solve for V. I get square root of 2e delta V over m. Nice little formula for figuring out how fast the electron's going when it leaves that little parallel plate capacitor, whose sole purpose in this setup is to accelerate the electron up to this speed v. By the way, we know all these numbers. The delta V is what they just call V there, 200 volts. Little e is the famous charge quantum, of course. And remember, we're talking about an electron, so the m is known. 9.11 times 10 to the minus 31 kilograms. So I will tell you what you get for that little v. I'm going to keep an extra sig fig. 8.382 times 10 to the 6 meters per second. pretty fast, but it is a very light object, an electron. That's how fast it's going then here. And all along that straight line up there until it enters the region where the field is, B1. Right there is where it first enters, yes? All right, let's figure out now how to get it to circulate in this circle, like so. There's its velocity right at the moment it enters the field, but it's going to circulate clockwise around the center of that half circle. So at that moment in time up there, it must have its magnetic force, FB1, I'll call it, downward at that one moment right there, when it starts that half circle. So let's just figure out then, from the magnetic force law, FB equals Q times V cross B, or negative little e times V cross B. Which way the magnetic field, it's got to be B1 here, doesn't it? FB1. Which way that B1's got to be pointed, so that I get the FB1 in the direction you see. And my contention is that we will conclude that the B1 must be into the screen. It is directed into the screen. That would be denoted with an arrow like that. Well, with an X, I should say. Now let me explain how I know that's the right direction. First of all, it's not that overwhelming to figure out, because the B1, we know it's only got two options. Out of the screen or into the screen. Okay, so we know the B1 is either out of the screen or into the screen. Let's figure out how we get the conclusion into the screen. Now, we have to get the FB1 downward there. See it there at that moment? But the particle is an electron, so its charge is negative. So that means the V cross B1 has to be upward. The V cross B1 has to be that way, so that when I flip the direction by 180 degrees, I get the correct direction for the FB1. And by the right-hand rule, if the V cross B1 has to be upward like that purple arrow, then the B1 has to be out of the screen. Okay, so V cross B1 is in the direction of the purple arrow, so that the FB1 is in the direction of the green arrow. So by the right-hand rule, you can deduce that the B1 must be into the screen in that region. Okay? And then we can figure out the radius of that circular motion, right? There's a radius there. I'll call it R1. And I'm just going to go straight to the formula we just derived. Right up there for the radius. mv over qb in this region here. So that'll be mv. I want the magnitude of the charge, little e, and the b I would use as b1. Now just plug in numbers. The m's for the mass of an electron. We just found the v. 8.382 times 10 to the 6 meters per second. The v is constant, remember. The magnitude, little e, is known. And B1 is 0.003 Tesla. So you put all those numbers in for R1. You'll get 1.59 times 10 to the negative 2 meters, which of course would be 1.59 centimeters. Okay, then it goes out of region 1 after a half circle, goes in a straight line to the left at this constant speed, little v, and it enters region 2, where it circulates around counterclockwise in a half circle. So now let's put the electron right there at the beginning of that half circle, in which point its velocity, v, is that way, but it's going to come around and downward, so the F magnetic, I'll label FB2 at the beginning here, is downward. And again, it's an electron, so if that's the direction of FB2, that's got to be the direction of V cross B2, right? Negative charge, the force is opposite to the direction of V cross B. What's got to be the direction of B2 then to give me V cross B2 upward? And my contention is that B2 must be coming out of the screen towards us in this region. So that when I do the right-hand rule, V cross B2, my thumb gives me the direction of the purple arrow, and then I reverse that direction to get the green arrow, which is the correct direction for FB2. And then, of course, I have a half circle here with some radius R2. And I can go straight to the formula for calculating that. MV over E B2. Okay? And I plug in the numbers, and I'll tell you what you get. You can check it for yourself. You get 7.95 times 10 to the minus 3 meters, or 7.95 millimeters. And now you found that radius. There's other things it wants to know. The time spent in the second magnetic field. How much time is it spent going around this half circle? Well, there's a couple of ways you could do it. One easy way is, since it's traveling at constant speed, the amount of time it takes, delta t, is the distance it goes. That's half the circumference of a circle over how fast it's going. Or you could use the period formula up above and take half of it, right there, that period formula. Be pi m over qb. So you can do it either way. You can try that. I'll tell you what you get. You get an amount of time of, look at this, 2.98 nanoseconds. Whew, that electron is going quickly, isn't it? And how fast is the electron going when it leaves this last field? It's still going at speed v. Remember, a magnetic field can only change the direction of a velocity, not its magnitude. Now, there's one more concept. All of this discussion was based upon an assumption that the charged particle had a velocity little v arrow perpendicular to that magnetic field. So if the red pen represents v and the green pen represents b, they are perpendicular. And then the motion you get for the particle is a nice circle. What if the velocity of the particle isn't exactly perpendicular to the magnetic field? How about if the velocity is like that of the particle? So it's moving to my right and up. Then it's got a component, the velocity, that's perpendicular to the magnetic field, and it's got a component parallel to the magnetic field. What kind of motion do you get then? And the answer is you get a trajectory called a helix. You get a helical trajectory. Okay? Like right there. This picture shows a magnetic field pointing upward in the plane of the screen. It shows a positively charged particle, charge q, with a velocity right here, v initially, that has a component parallel to the magnetic field, labeled v parallel, and a component perpendicular to the magnetic field, labeled v perp. And just to try to make that clear, here's a kind of a side view of the particle. Positive charge q, it's got this velocity v vector that makes an angle phi with the magnetic field direction. And then they've decomposed that velocity into a component parallel to the field, v parallel, and a component perpendicular to the field, v perp. Okay? So then what you get is you get two motions combined. The perpendicular component of the velocity, perpendicular to b, gives you uniform circular motion, just like we've been talking about. But you have to combine that with the effect of the parallel component of the velocity, v parallel. Well, but the first thing we learned in chapter 28, from the magnetic force rule, F equals Q times V cross B, that if the V and the B are exactly parallel, well, V cross B is zero. You get no magnetic force at all. So this component right here of the velocity, the v parallel, is completely unaffected by the magnetic field. So what you end up with altogether is uniform circular motion in a plane perpendicular to the direction of B, and straight line motion at constant speed parallel to B. And that's exactly what gives you a helix. A helix is circular motion combined with straight line motion perpendicular to the circle. And we can combine then these motions, right? For example, what's the radius? They call it little r. I tend to call it big R, of the circular motion part of the helix. It's the formula I just used up here. Put the star by for the radius, mv over qb. But, watch out, warning, danger. In that formula for the radius of the helix, the v that you have to use is the particular component v perpendicular, because that's the part of the velocity that gives you the circular motion. The period, that would be the time to travel once around in one revolution. So that would be like going from here in the helix, around, and around, until you are lined up again with vertically with where you started. That'd be the time once around. You can still talk about a period like that. And that would be 2 pi m over qb. Same formula I had up here for the period, because that formula doesn't depend on a v at all. And then you have one other thing called the pitch of the helix. Let me get rid of some stuff there so it's not so much clutter. The pitch of the helix, here it shows. P is just a distance. It's the distance between corresponding points on the helix, like there and there. It's kind of a way of thinking of how spread out are the circulations. It's called the pitch of the helix. And that's simply calculated. Take the component of the velocity v parallel times the time to go around once. V parallel. Okay? All right, so we're going to talk about that in class, the circular motion of a charged particle in a magnetic field. It is pretty important. It happens a lot in nature, particularly in Earth's atmosphere, and it happens a lot in physics labs. So let's end with just a little class engagement for Blackboard for circulating particle in a magnetic field. All right, in this situation, we have a proton, so we're telling you the charge. It's to be shot into a uniform magnetic field, B arrow. And there's the magnetic field vector. It's in plus y. See it right there? B arrow. And this proton is shot with a certain speed. That's fixed. But what we have a choice of is the angle of the velocity vector relative to the field direction. And the three choices are shown. So we can fire the proton with a velocity vector initially that's almost perpendicular to B, but not quite. We can shoot the proton with an initial velocity that's pretty much at 45 degrees between the magnetic field direction and the x-axis. Or we can shoot the proton with an initial velocity vector that's almost parallel to B, but not quite. That's what's going on. We are to rank these three choices, 1, 2, and 3, according to the radius of the proton's trajectory or path. Biggest radius first. Then rank those three choices according to the period of the proton spiraling in its helix. And then rank the choices according to the pitch of the proton's spiraling. So those are the questions that we answer for the class engagement. And as I said, we'll be talking about this in Friday's class. And that's all for this video.